We ended the previous lecture with the following questions. Given a square matrix A, when is A diagonalizable? And suppose that the matrix A is diagonalizable, how do we find the eigenvalues and eigenvectors of A? In this video and the next, we'll answer these two questions in detail. Okay, so to understand the conditions for diagonalizability of a matrix, these abstract tools of matrix polynomials and polynomial matrices are essential. So what do I mean by a matrix polynomial? A matrix polynomial is basically a polynomial where the coefficients are matrices, not arbitrary real numbers, right? So for example, if A0, A1, A2 up to AM are n by n matrices, then, well, in general there could be m by n matrices. Then f of x equal to A0 plus A1x plus A2x squared and so on plus amx to the m is a matrix polynomial of degree m. Right? At times we are also, so this is as opposed to a standard polynomial that you've seen with maybe real valued coefficients, such as this g of x, which is A0 plus A1 plus so on up to amx to the m, right? And basically they have very similar properties, except that the coefficients are matrices instead of real numbers, right? Okay, so we'll also be interested in polynomial matrices, where which correspond to matrices whose coefficients are whose entries are polynomials, right? So for example, this is a polynomial matrix: 1 plus x, 1 minus x, 1 plus x square, and x to the 4. Right? So this is an example of a polynomial matrix. Right? So why am I bringing this up? So the reason is that we know that if lambda is an eigenvalue of a matrix A, and let's suppose that V is a corresponding eigenvector, so V is one such eigenvector such that A times V equal to lambda times V. Now it's obvious that if we raise A to the, say, kth power, then A to the k V is equal to lambda to the k V. What this means is that if we take a polynomial of the form, so suppose we define f of x. So suppose we have the following polynomial, which is A0 plus A1 x and so on plus am to the m, and we define f of A to be A0i plus A1 A plus so on plus am A to the m. Then it's pretty clear that f of A, so this f of A is also a matrix. It's also an n by n matrix, which can be evaluated using this. So f of A times V will be equal to A0 plus A1 lambda plus, so it's A0 V plus A1 lambda V and so on plus am lambda to the m V, right? So this is basically equal to f of lambda, which is a scalar, times the vector V, right? So this is a useful property that we'll use in the coming lectures. All right, so with this we have essentially the background to understand the conditions under which a matrix is diagonalizable. Okay, so when is a matrix diagonalizable? So let's assume, so we start off with an n by n matrix A, and perhaps it has eigenvalues lambda 1, lambda 2 up to lambda k. So some of these eigenvalues could be repeated. So lambda 1 up to lambda k, where k is something which is less than or equal to n, right? And let us suppose that Wi is the eigenspace corresponding to the eigenvalue lambda I, right? So corresponding to each of these eigenvalues, we have eigenspaces W1, W2 up to Wk, right? Then it turns out that the following statements are equivalent. The first is, of course, what we're interested in, which is that A is diagonalizable. The second statement is that the characteristic polynomial of A, which is, so recall that the characteristic polynomial of A is the determinant of lambda or xi minus A, right? So this polynomial, suppose that we can write the characteristic polynomial as x minus lambda 1 raised to d1 times x minus lambda 2 raised to d2 and so on up to x minus lambda k raised to d lambda. So obviously the characteristic polynomial is a polynomial of degree n, so the di's must sum to n. So A is diagonalizable if and only if the characteristic polynomial of A is equal to this, that is x minus lambda I is raised to the power di, and the dimension of the eigenspace of corresponding to lambda I is also equal to di, right? So these are two different things, because so this di over here is defined in terms of the characteristic polynomial. So it's a very sort of algebraic quantity, and indeed di is called the algebraic multiplicity corresponding to the eigenvalue lambda I, and this quantity, the dimension of Wi, the dimension of the eigenspace, is a very geometric quantity, and therefore it's called the geometric multiplicity of lambda I. So A is diagonalizable if and only if the algebraic multiplicity is equal to the geometric multiplicity, right? An equivalent condition is that the sum of the geometric multiplicities is equal to n. So assuming that A is an n by n matrix. Okay. Right. So before we try to prove this statement, let us see some of its implications. Let's assume that these conditions are given to us, and see what the implications are, and how do we actually test whether a given matrix is diagonalizable or not. So let's start with some examples. Okay. So to work with these examples, we need an algorithm, and the algorithm is basically what is given by this particular result. So what do we have to do? We have to find the characteristic polynomial and the eigenvalues. So we have a general characteristic polynomial, and firstly you have to find the roots of the polynomial, right? So in general it's going to be sum over I going from 1 to n, let's say j going from 1 through n of aj x to the j. So that is what, sorry, j going from 0 n of aj x to the j. So the characteristic polynomial is going to be something of this form. The first objective would be to find the roots of the characteristic polynomial, and therefore write the polynomial as x minus lambda 1 raised to d1 times x minus lambda 2 raised to d2 and so on, x minus lambda k raised to the dk. Okay. So the first goal would be to write the characteristic polynomial in this form, and this gives us what the eigenvalues are and also what the algebraic multiplicities are, right? So once we do that, we need to find the geometric multiplicity, right? So and how do we do that? So So the geometric multiplicity corresponds to the eigenspace Wi, which is the set of all vectors x in Rn such that Ax is equal to lambda I times x, right? So this essentially corresponds to the null space of A minus lambda I times I, right? So the dimension of Wi is basically the nullity of the matrix A minus lambda I times I. And once you have the eigenvalues, you can obtain the eigenvectors as any basis corresponding. So to find the eigenvectors corresponding to the matrix, corresponding to the eigenvalue lambda I, all you need to do is find a basis for the null space A minus lambda I. Okay, so let's work out some simple examples, right? So let's start with an example that I had introduced in the previous lecture. So the matrix A is the following matrix. It is 1 1 0 1. We've already seen a proof that this matrix is not diagonalizable. So let's verify it using the conditions that we have. So the first thing we need to do is look at the matrix A minus. So first let's find the eigenvalues of this matrix, right? So the eigenvalues, the characteristic polynomial is determinant of lambda I or xi minus A I minus A. So it is equal to the determinant of x minus 1 minus 1 0 x minus 1, right? And this is equal to x minus 1 the whole square. So it has only one eigenvalue and it is repeated, right? So in this case lambda 1 is equal to 1 and d1 is equal to 2. The algebraic multiplicity corresponding to the eigenvalue 1 is equal to 2. So this matrix would be diagonalizable if the geometric multiplicity is also equal to 2. So the dimension of A minus lambda 1 times I should be equal to 2. So let's look at A minus lambda 1 is 1. So A minus I, which is 0 1 0 0, right? So clearly this matrix has rank 1, right? So this has rank 1 and therefore the nullity is equal to 1, just using the rank nullity theorem. So the dimension of W1 is equal to 1, which is less than 2, and therefore the matrix is not diagonalizable. Okay, so let's see a different example. So let's take A to be the matrix 1 2 2 1, right? So once again, let's try to compute the characteristic polynomial, which is the determinant of xi minus A, which is determinant of x minus 1 minus 2 minus 2 x minus 1, right? So this is x minus 1 whole squared minus 4. This is x square minus x minus 3. So if we try to set this to 0, then the eigenvalues turn out to be 2 plus or minus square root of 4 minus 12 divided by 2. So this is going to be 1 plus or minus square root of 8 divided by 2, which is going to be root minus 2. So this is 1 plus or minus I root 2, right? So obviously the determinant of so the eigenvalues of a matrix with real coefficients with real valued entries need not be real. So the eigenvalues could be complex, right? Because after all, we have a polynomial equation, and the solutions for a general polynomial with real valued coefficients could be complex. Okay, so these are the eigenvalues, and therefore this has no real eigenvalues, but it does have complex eigenvalues. So let's look at a slightly more complicated system. So okay, so going back, I didn't complete the solution. Right. So this has two distinct eigenvalues, and obviously there is at least one eigenvector corresponding to each eigenvalue, and therefore so the characteristic polynomial is basically x minus 1 plus I root 2 times x minus 1 minus I root 2, right? So it has two eigenvalues, two complex eigenvalues, and the corresponding algebraic multiplicities are 1. The geometric multiplicities are at least 1, and therefore this matrix is diagonalizable. And this is a symmetric matrix, and every symmetric matrix is always diagonalizable. All right, so let's take a 3 by 3 matrix, right? I won't work this out completely, but I encourage you to solve this by hand. You'll see that it has three eigenvalues: -3, 1, and 1. So 1 is a repeated eigenvalue. The one eigenvector corresponding to the eigenvalue -3 is the vector 1, 3, 1. Okay. So let's try to find the eigenvectors. Let's try to first check whether A is diagonalizable, and if so, try to find the eigenvectors corresponding to 1 and 1. Right? So for that, we need to look at A minus lambda 2 times I, so which is A minus I, which is going to be the matrix 4 minus 4, 4, 12 minus 12, 12, 4 minus 4, 4, right? So now if we do row reduction on this, we would get 4, 4. Okay, so this would be the row echelon form of this particular matrix, right? And this matrix has rank 1, nullity equal to 2, so the geometric multiplicity is equal to 2, which is also equal to the algebraic multiplicity. So this matrix is diagonalizable. Now we want to find the eigenvectors, or a basis for the eigenspace W2, right? So the basis is basically, to find the basis, we just need to find the set of all solutions of A minus I times x equal to 0, right? And one way to do this would be, so you already have the matrix in the row reduced form. So basically you have 4x1 plus minus 4 times x2 plus 4x3 to be equal to 0. We can take the pivot variable x1 to be fixed, and x2 and x3 to be the free variables. So for example, if I take x2 equal to x3 to be 1, then I get one vector which is 0, 1, 1. Right? And suppose I take x2 to be equal to say 2, and x3 to be equal to 1. Sorry, x3 to be equal to 2. Sorry, x2 equal to 2 and x3 equal to 3. Then x1 would be equal to -1. Right? Okay. So these are two vectors which are obviously linearly independent, and therefore they form a basis for the null space of A minus I, and therefore we already have 3 linearly independent. So you can also check that the vector 1 3 1, 0 1 1 and minus 1 2 3 are these 3 vectors are linearly independent, and therefore they form a basis for R3, and these 3 are going to be the eigenvectors corresponding to the matrix A. Okay, so now now that we have some idea of how do we find the eigenvalues and eigenvectors, we also want to know how do we decompose. So recall that in the last lecture I was talking about the Eigen decomposition. So there's a canonical form. So every matrix A, every diagonalizable matrix A can be written as P inverse dP, or equivalently we can write any diagonal matrix. So I can write D as P D P inverse, or Q inverse dQ, where Q is P inverse, right? And the goal is to find out what D is and what P is, right, or what Q is. So we already know that D is the diagonal matrix consisting of the eigenvalues of A. This is lambda 1, lambda 2 up to lambda n. So some of these eigenvalues could be repeated. I'm just writing these down. Now how do we find Q or P? I claim that I can take Q to be equal to V1, V2 and Vn, where Vi is the eigenvector corresponding to the eigenvalue lambda I. Okay. So if I take Q to be the following, then I claim that D is equal to Q inverse DQ. Q inverse AQ. Okay. So the claim is that if I take lambda to be the diagonal matrix of eigenvalues, and I take Q to be the n by n matrix, where the ith column is equal to the eigenvector corresponding to lambda I, then Q inverse AQ is equal to D. I won't prove this here, but I want you to work this out and prove that this is indeed the case. And the trick here is to evaluate this one at a time. So find AQ and then find Q inverse AQ and show that this is actually diagonal.